Welcome back to Prestressed concrete structures. This is the fifth lecture of Module 9 on special topics. In today's lecture, we shall cover compression members. After the introduction, we shall study about the analysis, development of interaction diagram, and effect of prestressing force. Prestressing is meaningful when the concrete in a member is in tension due to the external loads. Hence, for a member subjected to compression with minor bending, prestressing is not necessary. But when a member is subjected to compression with substantial moment under higher loads, prestressing is applied to counteract the tensile stresses. Examples of such members are piles, towers, and exterior columns of framed structures. Earlier, when we studied the behavior of axial members, we had known that the prestressing is effective only when the concrete is under tension. In fact, prestressing may be harmful if the concrete is under compression because the compressive capacity of the member gets reduced. Thus, prestressing is applied to mostly tension members, but if a compression member is subjected to substantial moments along with compression, then prestressing may be meaningful. Thus, for compression members, prestressing is applied to piles, towers, or columns in a building only if they are subjected to high moments due to lateral forces. As the seismic forces are reversible in nature, the prestressing of piles or columns is concentric with the cross section. Some typical cross sections are shown below. The one in the left is a partially prestressed column where we are having non-prestressed reinforcement at the four corners, and we also have prestressing tendons at the center. The two figures on the right are piles. The first one is a circular section and the second one is a hexagonal section, and here the prestressing tendons are along the perimeter, but the effect of prestressing force is concentric to the section. This is a figure which shows the lowering of the reinforcement cage for a pile. Since a prestressed member is under self-equilibrium, there is no buckling of a column due to internal prestressing with bonded tendons. In a deflected shape, there is no internal moment due to prestressing. The justification is explained in the next figure. If a column or a pile is subjected to an axial force, then when it gets deflected, there will be a moment due to the deflected shape. For a deflection of delta at the middle, the moment at mid height is represented as P delta. This happens under the axial compression, whereas for an internal prestressing, we observe that even under the deflected shape, the internal prestressing is under equilibrium with the tension in the prestressing tendon, and there is no internal moment generated under the deflected shape. Thus, in the free body sketch of figure 9EA, the external compression P causes an additional moment due to the deflection of the member. The value of the moment at mid height is P delta. This is known as the member stability effect, which is one type of P delta effect. If this deflection is not stable, then buckling of the member occurs. Thus, the external compression can cause buckling of a member depending upon the slenderness ratio. In the second case, for a prestressing, in the free body sketch, there is no moment due to the deflection of the member under the prestressing force, since the compression in concrete, which is C, and the tension in the tendons, which is T, balance each other. When the additional moment due to deflection of the member is negligible, the member is termed as short member. The additional moment needs to be considered when the slenderness ratio of the member is high. The slenderness ratio is the ratio of effective length and lateral dimension. This type of members are termed as slender members, where the additional moment needs to be considered. In the analysis of a slender member, the additional moment is calculated by an approximate expression or second order analysis. In this module, only short members will be considered. Thus, if we have a slender member depending upon the slenderness ratio greater than a certain value, then we need to account for the additional moment generated due to the external compression, and this can be estimated by an approximate expression or by second order analysis. But in this lecture, we are considering only short members where the additional moment due to the deflection of the member is negligible. Next, we are moving on to the analysis of compression members. The stress in the section can be calculated as follows. Fc is equal to P0 divided by A. Here A is the area of concrete and P0 is prestress at transfer after short-term losses. Thus, after the concrete is cast and then the prestressing is transferred to the member, we find that the stress in the member is compressive and it is uniform, since the prestressing is concentric, and this compression is given as the prestress at transfer, which is P0, divided by the area of the concrete, which is A. In this equation, it is assumed that the prestressing force is concentric with the cross section. For members under compression, a compressive stress is considered to be positive. In this lecture, we shall consider that a compressive stress is positive and a tensile stress is negative. This is the convention which is used for compression members. The permissible prestress and the cross-sectional area are determined based on the stress to be within the allowable stress at transfer FCC allowable. Thus, given the compressive stress to be within the allowable value, we can determine P0 and A, a suitable combination of the two variables. Next, we are moving on to the analysis at service loads. The analysis is analogous to members under flexure. The stresses in the extreme fibers can be calculated as follows. Fc is equal to Pe divided by A plus N divided by At plus minus M times C divided by It. The first term is due to the prestressing force, which is now the effective prestress under service loads. The second term is due to the external compression, which is represented as N, and the third term is due to the external moment, which is represented as M. In this equation, the external compression for a prestressed member is denoted as N and is concentric with the cross section. The eccentricity is considered in the external moment M. Also, A is the area of concrete, AT is the area of the transformed section, C is the distance of the extreme fiber from the centroid of the section, which is CGC, IT is the moment of inertia of the transformed section, PE is the effective pre-stress. The value of FC should be within the allowable stress under service conditions. Next, we are moving on to the analysis at ultimate. When the average pre-stress in a member under axial compression and moment is less than 2.5 Newton per millimeter square, clause 22.2 of IS 1343-1980 recommends to analyze the member as a reinforced concrete member, neglecting the effect of pre-stress. Thus, if the pre-stress is small, then the code allows us to analyze the pre-stressed member as a reinforced concrete member with just the amount of the external load acting on it. If the amount of pre-stress is greater than 2.5 Newton per millimeter square, then we analyze the pre-stressed member including the pre-stress and with the help of interaction diagrams for the ultimate limit state. At the ultimate state, an interaction diagram relates the axial load capacity, which is represented as NUR, and the moment capacity, which is represented as MUR. The R stands for resistance and the U stands for ultimate. It represents a failure envelope. Any combination of factored external loads NU and MU that fall within the interaction diagram is safe. Let us understand this by the help of a sketch. A typical interaction diagram is shown below. The shaded area inside gives combinations of external loads MU and NU that are safe. Thus, this boundary is a failure envelope, and any combination of the external loads which fall within this boundary is safe, and a combination which falls outside this boundary is unsafe. Now, in this boundary, we have two types of failure conditions. One is the compression failure and the other is the tension failure. The transition between them is called the balanced failure. The radial line in the previous sketch represents the load path. Usually, the external loads increase proportionally. At any load stage, M and N are related as follows. M is equal to N times En. Here, En represents the eccentricity of N, which generates the same moment M. The slope of the radial line represents the inverse of the eccentricity, which is 1 by En. Thus, in most of the cases, the axial load and the moment, when they increase proportionately, and hence the load path is a straight line which passes through the origin and moves towards the failure envelope. The slope of that line is given as 1 by En, where En is the ratio of the moment M and the axial force N. At ultimate, the values of M and N, which are then represented as MU and NU respectively, correspond to the values on the interaction diagram. Thus, as the load increases along the load path, and finally, when at ultimate the load state falls on the interaction diagram, then a failure occurs. For high values of n as compared to m, that is En is small, the concrete in the compression fiber will crush before the steel on the other side yields in tension. This is called the compression failure. For high values of m as compared to n, that is En is large, the concrete will crush after the steel yields in tension. This is called the tension failure. The transition of these two cases is referred to as the balanced failure when the crushing of concrete and the yielding of steel occur simultaneously. Thus, the significance of compression failure is that the concrete is crushing before the steel has a chance to yield, and the tension failure means that the concrete is crushing after the steel has yielded, and the transition between them is called the balanced failure, where the crushing of concrete and the yielding of the steel occur simultaneously. For a prestressed compression member, since the prestressing steel does not have a definite yield point, there is no explicit balanced failure. Unlike the steel used for reinforced concrete member, which tend to have a sharp yield point, such as mild steel, unlike that, the prestressing steel does not have a sharp yield point. Hence, the definition of a balanced failure is not explicit for a prestressed compression member as compared to our reinforced concrete member under compression. Next, we shall learn about the development of interaction diagram. An interaction diagram can be developed from the first principles using the nonlinear stress strain curves of concrete under compression and steel under tension. Several sets of NUR and MUR for given values of En or XU are calculated. The distance of neutral axis from the extreme compressive phase is denoted as XU. Partial safety factors for concrete and prestressing steel can be introduced when the interaction diagram is used for design. Thus, the interaction diagram is developed by calculating values of the capacities NUR and MUR for a given eccentricity En. Also, we can do the same calculations for a given value of XU, where XU is the depth of the neutral axis from the extreme compressive phase. Once we calculate a set of NUR and MUR values, we can join those points to get the interaction diagram for that particular member. If we use partial safety factors, then this curve can be used for design. Here, the procedure is illustrated for a rectangular section with prestressed tendons placed at two opposite faces symmetrically and without non-prestressed reinforcement. Thus, we shall study the development of the interaction diagram for a rectangular section whose lateral dimension about the direction of bending is the depth d and whose lateral dimension transverse to the direction of bending is b. The prestressing tendons are placed symmetrically about the centroid. The group on the left is denoted as AP1 and the area on the right is denoted as AP2. D1 and D2 are the distances of AP1 and AP2 respectively from the CGC. The notations thus used are as follows. B is the dimension of section transverse to bending. D is the dimension of section in the direction of bending. AP1 is the area of prestressing tendons at the tension phase. AP2 is the area of prestressing tendons at the compression phase. D1 and D2 are the distances of centers of AP1 and AP2 respectively from the centroid of the section which is CGC. For a prestressed member, the strain compatibility equation is necessary. It relates the strain in a prestressing tendon with that of the adjacent concrete. Due to a concentric prestress, the concrete at a section undergoes a uniform compressive strain. With time, the strain increases due to the effects of creep and shrinkage. At service, after the long-term losses, let the strain in concrete be epsilon Ce. Let the strain in the prestressing steel due to effective prestress be epsilon Pe. Thus, just due to prestressing, the section undergoes a uniform compression which increases with time due to the losses, and after the losses, let the compressive strain in the concrete be epsilon Ce and the tensile strain in the prestressing tendons be epsilon Pe. This is the strain diagram that we are observing due to the prestressing force alone under service conditions. The strain compatibility equation for the prestressed tendons is then given as follows: epsilon Pe is equal to epsilon C plus delta epsilon P. Thus, under any load, the strain in the prestressing steel epsilon P is equal to the summation of the strain in the concrete, which is epsilon C at that level of the prestressing steel, plus this strain differential, which we denote as delta epsilon P. Delta epsilon P is calculated as epsilon Pe minus epsilon Ce. Thus, we calculate that what is the uniform compressive strain in concrete under service conditions due to the prestressing force, what is the tensile strain in the tendons under service conditions. We take their difference, get this strain differential, and we add this strain differential to the strain in concrete to get the strain in the prestressing steel at that level. This is called the strain compatibility equation, which relates the strain in the concrete with the strain in the prestressing steel, which are lying at the same level. The following stress strain curve for concrete under compression is used. It is parabolic and then it is constant up to a strain of 0.0035. The stress strain curve for the prestressed tendon under tension can be expressed in the following terms. This curve is not an elastoplastic behavior. It has a gradual transition from the elastic behavior with increasing plastic strain, and this curve is symbolically represented as Fp is equal to a function of epsilon P. The calculation of MUR and NUR for typical cases of En or Xu are illustrated. The typical cases are as follows. First, the case of pure compression, where En is equal to 0 and Xu is equal to infinite. Second, full section under compression, where En can vary between 0.05 d and less than En corresponding to Xu is equal to d, and Xu is greater than or equal to d. Third is part of section which is under tension. Here En is greater than the value corresponding to Xu equal to d, but it is less than infinite, and Xu is less than d. And finally, we have pure bending, where En is equal to infinite and Xu is equal to x min, which is the minimum value of Xu. We shall study these cases as we move on. In addition to the above cases, the case of pure axial tension is also calculated. the straight line between the points of pure bending and pure axial tension provides the interaction between the tensile force capacity and the moment capacity. Thus, this part of the interaction diagram is in the lower quadrant, where the tensile axial force is given by a negative value. We calculate the moment capacity of the section under pure bending, we calculate the tensile force capacity of the member, and then we plot these points, join them by a straight line, and like that we get the interaction diagram for the quadrant which is for the tensile force applied on the section. Any combination of external loads lying within the green region is safe. Next, we are moving on to the development of the interaction diagram for each of the typical cases separately. First, the pure compression. Under pure compression, the strain profile is constant, and at ultimate the strain is given as minus 0.002. The eccentricity is 0 because there is no moment, whereas the depth of the neutral axis from the compression phase is infinite. Now the stress profile is, we have a stress of 0.447 FCK uniform along the concrete, and the stress in the prestressing tendons are denoted as FP1 and FP2, which we shall calculate from the strains epsilon P1 and epsilon P2. From the strain profile, thus we go to the stress profile, and then we go to the force diagram, where the compression in concrete is denoted as Cu and the tension in the prestressing tendons is denoted as Tu1 and Tu2 for AP1 and AP2 respectively. The forces are as follows: Cu is equal to 0.447 FCK times Ag minus AP, Tu1 is equal to Tu2 is equal to AP1 times FP1 is equal to AP1 times EP times minus 0.002 plus delta epsilon P. Thus, the term in the bracket represents the strain compatibility condition that we have used to calculate the strain in the prestressing steel from the strain in the concrete, which is minus 0.002. The steel is in the elastic range, and hence we have used the Hooke's law, which is the stress is equal to the modulus times the strain in the steel. The total area of prestressing steel is denoted as AP, which is equal to AP1 plus AP2, and the area of the gross section is denoted as AG is equal to BD. Thus, we can calculate the values of Cu and Tu1 and Tu2 given the geometric variables of the section and the material properties. Next, we are calculating the axial load capacity. The moment capacity MUR for this case is 0, there is no moment, whereas the axial load capacity is given as Cu minus Tu1 minus Tu2. Again, remember that a compression is considered to be positive and a tension is considered to be negative for compression members. And once we substitute the values of Cu, Tu1 and Tu2, we get an expression of NUR. In design, to approximate the effect of moment for eccentricities En less than or equal to 0.05 d, the axial force capacity is reduced by 10%. In design, if a member has small moment applied on the section, then we try to bypass using the interaction diagram by considering a reduced axial force capacity and neglecting the effect of moment. this is allowed when the eccentricity is less than 5% of the dimension d, and then the axial force capacity is reduced by 10% to get an expression of NUR. In that case, NUR is given as 0.4 FCK times AG minus AP minus 0.9 AP times EP times EP minus 0.002 plus epsilon CE. Next, we are moving on to the case of a full section under compression under simultaneous axial load and moment. Note that here this is applied when the eccentricity is larger than 0.05 d, but smaller than the case when xu is equal to d. Thus, whenever xu is equal to or greater than d, the full section is under compression. Let us try to understand the strain diagram, that the depth of the neutral axis is outside the section, that means the full section is under compression, and it is assumed that the strain diagram pivots about a point which is at a distance 3/7 d from the extreme compression phase, where the strain is minus 0.002. This is an important assumption to get the strain diagram for a given value of xu is equal to k times d. Note that here k is greater than 1. Now, given the strain diagram, we calculate the stress diagram. Here the parabolic part of the stress diagram in concrete goes outside the section, hence the computations are a bit more involved. We need to calculate the area under this curve, and for that we first calculate the area under the rectangular region, from which we subtract the area of this shaded part, which we denote as A sector. We also calculate the tension in the prestressing tendons from the strains. The limiting case for full section under compression corresponds to xu is equal to d when the neutral axis lies at the left edge of the section. The strain diagram pivots about a value of minus 0.002 at 3/7 d from the extreme compression phase. To calculate Cu, first the value of g is evaluated. This g is the intercept of the parabolic curve from the value of 0.447 FCK. Based on the second order parabolic curve for concrete under compression, the expression of g is as follows. This expression can be derived by assuming a second order parabola. G is equal to 0.447 FCK times 4/7 d divided by xu, which is equal to kd minus 3/7 d. This whole term is within bracket and raised to the power 2. This can be simplified to g is equal to 0.447 FCK times 4 divided by 7k minus 3 whole square. The area of the sector is as given as follows. This is the area of a parabolic section, and it is given as 1/3 times g times the distance to the apex from the base, which is 4/7 d. Thus, the area of the sector is equal to 4/21 g times d. Thus, once we know g, we can calculate the area of the sector. The distance of the centroid of this area from this apex is denoted as x prime, and this is equal to 3/4 of 4/7 d, which is equal to 3/7 d. Then Cu is given as the area of the rectangular section 0.447 FCK times d minus area of the sector A sector whole times B. Once we substitute the value of the area of the sector, we get an expression of Cu for the given value of K. Next, we are finding out Tu1, which is AP1 times FP1, and again here Tu1 is within the elastic limit, and we can substitute the value of the strain in the concrete by this expression, which we can derive from the strain diagram. That means once we know the strain in the pivot point and we know that the strain at the neutral axis is 0, from the similarity of the triangles we can find out what is the value of epsilon C1 at the distance of xu minus d by 2 plus d1. Thus, this expression has come from the similarity of the triangles. To the strain of the concrete, we add the strain differential to get the strain in the prestressing steel. From that, we calculate the stress, and then we calculate the force in the prestressing steel AP1. Similarly, we can calculate Tu2, which is from the strain in the concrete at the level of AP2, and here also we find that the strain at epsilon C2 can be determined from the similarity of the triangles. That means based on this value of minus 0.002 at the pivot point, we can calculate what is the strain at this level, and again this expression is derived from the similarity of triangles. Thus, after these calculations, the moment and the axial force capacities are as follows: NUR is equal to Cu minus Tu1 minus Tu2, and MUR is equal to MC plus MP. The MC is the moment due to the force in the concrete, and MP is the moment due to the forces in the prestressing tendon. The expression of MC and MP about the centroid of the section are given below. Anticlockwise moments are considered to be positive in this derivation. MC is equal to 0.447 FCK times dB times 0. This is the area of the rectangle whose centroid lies at the centroid of the section, and hence this rectangular stress block does not create any moment about the centroid. The MC then is due to only the area of the sector, A sector, which is given as A sector times B within bracket x prime plus 3 by 7 d minus d by 2. That is the distance of the centroid of the sector from the centroid of the cross section. Thus, this term on the right hand side gives the value of MC, which when simplified is equal to 10 divided by 147 g d square times b. MP is given by taking the moments of Tu1 and Tu2 based on the centroid, and since these are at distance d1 and d2, MP is equal to Tu1 times d1 minus Tu2 times d2. Next, we are moving to the case where part of the section is under tension. Note that in the strain diagram, now on the left hand side we have some tension. En is less than the value corresponding to xu is equal to t, whereas En is less than infinite, which is for the case of pure bending. Xu, which is the depth of neutral axis, is lower than d. Once xu is lower than d, we have some tension on the left side. We have from the strain diagram, we get the stress diagram. Note that the extreme compression is now 0.0035 and the stress diagram is similar to a reinforced concrete section. That means once the section cracks, the analysis is similar to a section under flexure. The forces are as follows: Cu is equal to 0.36 FCK times Xu times P, which is the resultant of the stress block in concrete. Tu1 as before is given as AP1 times FP1. Now here FP1 should be calculated from the stress strain curve. Now the concrete around AP1 is under tension and the prestressing tendon may go to the yield region, and hence we should not use the elastic values without checking whether the steel is yielding or not. For Tu2, of course, the steel need not yield and we can use the elastic relationship. The strains epsilon C1 and epsilon C2 are calculated from the strain diagram as follows. Again, these expressions are based on the linearity of the strain diagram, and from similarity of triangles we can find out that given this extreme strain minus 0.0035 and given the location of the zero strain, which is Xu, we can find out what is epsilon C1 from the similarity of the triangles. Similarly, we can find out what is epsilon C2 knowing these distances. Thus, given the distances of AP1 and AP2 from the neutral axis, we can find out what is the value of epsilon C1 and epsilon C2. From epsilon C1 and epsilon C2, we calculate epsilon P1 and epsilon P2, from which we calculate FP1, FP2, and then we get the forces, and finally the moment and the axial force are given by these equations, which is same as we had seen before, that NUR is equal to Cu minus Tu1 minus Tu2 and MUR is equal to MC plus MP. The expression of MC about the centroid is given by the stress block times the lever arm, which is d by 2 minus 0.42 Xu, and the expression of MP is same as before. Finally, we are coming to the case of pure bending, where the eccentricity is now infinite because there is no axial force coming and the depth of the neutral axis has the minimum value for all these cases. The value is Xu is determined by trial and error from the condition that the sum of the forces is 0. Thus, we write the generic expression Cu minus Tu1 minus Tu2 is equal to 0. We substitute the values of Cu, and then from this we get an expression of Xu. The strains epsilon P1 and epsilon P2 are calculated from the strain compatibility equations. The strain epsilon P2 is within the elastic range, whereas epsilon P1 may be outside the elastic range. The stresses FP1 and FP2 are calculated accordingly from the stress versus strain relationship of prestressing steel. The steps for solving Xu are as follows. Assume some value for Xu, say 15% of the total depth. Then determine epsilon P1 and epsilon P2 from strain compatibility. Determine FP1 and FP2 from the stress versus strain relationship for the prestressing tendon. Calculate Xu from the expression which satisfies that the axial force in the section is 0, and then compare this Xu with the assumed value. If it does not satisfy, iterate till we converge. That means we are satisfying the condition that the axial force in the section is equal to 0. The moment and the axial force capacities are as follows. The axial force capacity is 0 for pure bending, and the moment is equal to MC plus MP, where the expressions of MC and MP are same as the previous case. Last, we come to the axial tension, where the moment and axial force capacities are given directly. the cracked concrete is neglected in calculating the axial force capacity. Thus, the axial force capacity is equal to minus 0.87 times FPK times the total prestressing steel, which is AP, and MUR is equal to 0. The above sets of NUR and MUR are joined to get the interaction diagram. Let us calculate the design interaction diagram for the member given below. The member is prestressed using 8 strands of 10 mm diameter. The strands are stress relieved with the following properties. The tensile strength is equal to 1750 Newton per millimeter square. The total area of tendons is 8 times 51.6 is equal to 413 millimeter square. The effective pre-stress is 1034 Newton per millimeter square. Modulus of elasticity EP is 200 kilonewton per millimeter square. The strain under FPE, which is epsilon PE, is given as 0.0052. The grade of concrete is M40, and the strain under FPE, which is epsilon CE for the concrete, is 0.0005, and the dimensions of the sections are as follows: D is equal to 300, B is equal to 300, and the distances from the edges to the center of the prestressing steel is 50. First, calculation of geometric properties and strain compatibility relationship. AG is 90,000 millimeter square, AP1 and AP2 is 206 millimeter square, D1 and D2 is equal to 100 millimeters. Delta epsilon P is equal to 0.0052 minus 0.005, which is equal to 0.0047. Thus, our strain compatibility equation is epsilon P is equal to epsilon C plus 0.0047. We are calculating for the case of pure compression. For this case, MUR is equal to 0. We are calculating the expression of Cu from the previous expression, and it is equal to 1601.8 kilonewtons. Tu1 and Tu2 comes out to be 111.5 kilonewtons. We calculate the value of NUR, and we get NUR is equal to 1378.8 kilonewtons. If we reduce by 10% to consider eccentricities less than 0.05 T, then NUR is equal to 1204.9 kilonewtons. Next, we are calculating for the full section under compression. We are selecting XU is equal to 400 millimeters. That means the depth of the section is 300, whereas XU lies 100 outside the section, where K is given as 4 by 3. We can calculate the value of G by the previous expression, and then we get the value of Cu. Again, substituting in the previous expression, we get Cu is equal to 1486.9 kilonewtons. We are calculating the strain in AP1, from which we get Tu1 is equal to 148.4 kilonewtons. Similarly, we are calculating the strain in AP2, from which Tu2 is equal to 87.5 kilonewtons. Thus, NUR is equal to Cu minus Tu1 minus Tu2. Substituting that, we get NUR is equal to 1251 kilonewtons. We can limit that NUR to the value corresponding to E is equal to 0.05 D, and that value is 1240.9 kilonewtons. We are calculating the value of MC. From the previous expression, we get MC is equal to 13.1 kilonewton meters, and MP we get 6.1 kilonewton meters. When we add them up, we get MUR is equal to 19.2 kilonewton meters. Thus, for this case, we have got the values of NUR and MUR. We are selecting another case where XU is equal to 300. That means the neutral axis is lying right at the edge of the section. Here K is equal to 1, and by similar calculations we can find the values of G, Cu, Tu1, Tu2. NUR comes out to be 1060.6 kilonewtons and MUR is equal to 42.5 kilonewton meters. Next, we are moving on to the case of a part of a section under tension. We are selecting XU is equal to 200 millimeters. Note that now the neutral axis lies within the section. Cu is given by this expression, which is equal to 864 kilonewtons, and we are calculating epsilon C1 from the strain diagram. Given the two distances 200 and 50, we can calculate what is the value of epsilon C1. Then epsilon P1 is equal to epsilon C1 plus the strain differential 0.0047, which is equal to 0.056. Since the strain is within the elastic limit, now the elastic limit is given as 0.87 of 0.8 FPK divided by epsilon P, which is equal to 0.0059. Note that epsilon P1 is less than epsilon Py, and hence we can use the elastic relationship. Fp1 is equal to Ep times epsilon P1. We get 1150 Newton per millimeter square, from which we get Tu1 is equal to 230.1 kilonewton. We can calculate the strain in AP2 similarly from another strain diagram from the similarity of the triangles, and from epsilon C2 we calculate epsilon P2, and that is equal to 0.0021. Fp2 is calculated from the elastic relationship, and Tu2 is equal to 85.9 kilonewtons. Thus NUR is equal to 548 kilonewtons. MC, we can substitute the values, and that is equal to 57.0 kilonewton meter. MP is equal to 14.4 kilonewton meter. Thus MUR is the summation of MC and MP, which is equal to 71.4 kilonewton meters. For the pure bending case, NUR is equal to 0, and now we are trying to solve the equations by trial and error. We select XU is equal to 100, we calculate the value of Cu, which is equal to 432 kilonewtons. We are calculating the values of epsilon C1 from the strain compatibility relationship. Then we calculate epsilon P1 from the stress strain curve. We find that Fp1, now this stress strain curve has to be used for the stress relieved type of steel, and Fp1 is equal to 1492 Newton per millimeter square. Tu1 is equal to 308 kilonewton. Similarly, we can calculate epsilon C2 from the strain diagram, and we calculate epsilon P2, from which we can calculate Fp2, and finally Tu2 is equal to 120 kilonewton. Tu1 plus Tu2 is equal to 428, which is close enough to Cu. Hence, the trial section of XU is satisfactory. MC, by substitution of the values, is 46 kilonewton meter, and finally we get MUR is equal to 65.4 kilonewton meters. For axial tension, MUR is equal to 0 and NUR is equal to minus 616.2 kilonewtons. The above sets of NUR and MUR are joined to get the following interaction diagram. The limit on axial force capacity to consider the effect of eccentricity less than 0.05 d is not shown in this diagram. This is the interaction curve for the section, and once we have plotted the points, we get this failure envelope. To see the effect of prestressing force, let's compare the results with two equivalent reinforced concrete sections. For the first section, the blue line is represented is the prestressed concrete section. The pink line above is a reinforced concrete section with the same flexural capacity, and the yellow line is a reinforced concrete section with the same axial load capacity. Along the interaction curve for the prestressed concrete section, the interaction curves for the two reinforced concrete sections are plotted. The section denoted as RC1 has the same moment capacity at zero axial force. The section denoted as RC2 has the same axial force capacity at zero moment. The gross section of RC1 is same as that of the PC, but the section of RC2 is smaller. Comparing the curves for PC and RC2, it is observed that if the moment demand is small, then a smaller reinforced concrete section is adequate to carry the axial force. Of course, with increasing moment, the flexural capacity of the prestressed section is higher. Comparing the curves for PC and RC1, it is inferred that for the two sections with the same flexural capacities, the axial load capacity of a prestressed concrete section is less. Thus, prestressing is beneficial for strength when there is occurrence of large moment in addition to compression. Such a situation arises in piles or columns subjected to seismic forces. Of course, prestressing is beneficial at service loads due to reduced cracking. Non-prestressed reinforcement may be used for supplemental capacity. Today we covered the compression members. After the introduction of the different types of application of prestressing in compression members, we went on to the analysis of compression members. We first saw the analysis at transfer, then at service, and finally at the ultimate state. For the ultimate state, we need interaction diagrams, and we learned about the development of the interaction diagrams. And we came to know that the effect of prestressing is beneficial only when there is high moment along with the axial compression. Otherwise, it may not be economical. With this, we are ending the module on compression members. Thank you.